no actual tests taken. Okay, so I want to start with this exercise. And the first thing we're going to do is we're going to consider the radiative transfer equation, because I think it's really important to jump right in and do something really hard in the third slide. Okay, so what I want you to do is take out a piece of paper and pencil, or you can have a digital one. And I want you to sketch a diagram or write the equation for the radiative transfer equation.
I swear I didn't put her up to this.
Okay, I'm kidding. What I really want you to do is take this knowledge survey. So take one of these. Because that's sometimes how it starts in class, right? You already start like, oh God, right? Or you're like, oh, cool, I did that last week, right? And you're the person smiling, but the person next to you might not be smiling, right? So what I want you to do is answer the first part A, where I say, sketch the diagram and write an expression for the radiative transfer equation. And I want you to say, like, circle one of these, like, oh, I know just what to do. Man, I am on this, right? That's my thesis. Or, God, I don't remember what that third term was. Or, I'll try anything. I'll get something down. I have no idea where to start. What is the radiative transfer equation? So just for yourself, circle one of those and flip it back over, okay? It turns out that a knowledge survey is about 95% effective in terms of assessing your understanding of something. Your assessment of how well you understand something is, you're right on. So if you're like, I'm a C, you probably are if I gave you a test on that, right? Like, so knowledge surveys, you don't actually have to do the work. You just have to sort of be really honest about your self-assessment. And it's really helpful. And so the reason why I use these in class is so that I can say, wow, everyone's down here, so I know where to start, right? So it's really helpful for the instructor to know where to start. All right, so let's consider the light field in the ocean. And I love this. You probably, if you looked over any of the slides, you've seen this before. And I love this picture because you can basically give an entire class on this picture. And in fact, you pretty much will, right? So sunlight coming into the ocean, bright spots, dark spots, rays, changing magnitude, will be changing color. And so we want to think about this forward and inverse approach. And have you heard about this today yet already? We're going to do it again. Okay. This is from a really old but great figure from Borman Huffman, talking about the direct model or the forward model. And so what that says is, I know I have a dragon, right? It could be this picture or it could be this picture, right? I have this dragon, and what are its tracks going to look like? It is going to make prints. It is the actor. It is the thing, the driver. In the forward model, if I look at this dragon and I look at its feet, I should be able to predict the tracks that it makes, okay? So maybe the tracks look like this, because it's a model, so it's sort of like a cartoon sketch. Okay? So knowing the driver, we can predict what happens. And then with the inverse approach, you just get the tracks. And so the tracks are, how do I predict my dragon, right? So if I see these tracks, and these are actually the tracks of a dragon. I just never really thought about the tail, right? Right? I know, it's so cool. So from that, what kind of dragon? Well, is it this little dragon, or is it this one, right? So we have to think about, given this, we have a range of options, and that's that hard inverse problem that we're talking about. The most uncertainty is going in the inverse direction. And so if we think about this optically in our forward model, we measure absorption and scattering, and that's the dragon. We're measuring the driver, the thing that determines what the oceanic light field is going to look like, right? So we have the inherent optical properties, and we can get to the radiometric variables through the radiative transfer equation. It's a forward model. In the inverse sense, and we can also, not only the radiometric variables, but the properties that are derived from them. If you don't know the relationship here, believe me, you'll get there. We'll get That's the forward model. And the inverse model, again, we're observing the effect and trying to get at what the drivers were. Tracks, dragon. Okay. So today I just want to talk a little bit about this.
I have a quick question.
Yeah.
Will these slides be available?
They are.
They are.
They're on.
It would be 5 minutes on the website. Perfect. Thank you.
Although I like it better when you just listen.
Yes.
Yeah, right. So you don't have to write things down. Yeah. Okay. So the radiative transfer equation is a forward model, and it describes how sunlight propagates from its source. But we have to define our source. Is our source at the sun? Is it at the top of the atmosphere? Is it at the surface of the ocean? Is it below the surface of the ocean? What's our source? And how that light gets formulated into the ocean and where we're going to measure it. Okay, so let's talk about the source. I also love this picture a lot. I use this in almost all my classes that I can manage to shove it in. So this is from the space station, and it's looking at the Earth and the sun, and this is above the atmosphere. It was during a spacewalk. Wouldn't that be awesome? So what I want you to do is let's make some observations about the source. So tell me some things that you see. I said, okay, we're going to be tracing the sun into the ocean. We want to start at the source. Tell me about the source. Yeah.
It's white.
It's white. Is that correct? You guys, is the sun white? How do you know? Did you look at it? Don't ever look at the sun. Yeah, it looks white, right? It looks white. What else?
It's bright.
It's really bright, right? In comparison to everything around it, it's really bright.
It has rays.
It has rays.
Has a uniform radiation.
It has what?
Uniform radiation.
Unique.
Uniform radiation.
Oh, yes. Uniform radiation. It's sort of relatively, if you sort of looked in spheres, concentric spheres coming away, it would be relatively uniform in those spheres. What about space?
It's very dark.
It's very dark. Yeah. There is no light really out here, right? So there's this extreme contrast between the sun and space. Excellent. All right, so it turns out, in one slide, any object that's above 0 Kelvin emits radiation, right? And Planck's law tells us, describes in this, sort of odd equation that's actually so brilliant. It's that the spectrum of the electromagnetic emission is dependent upon the temperature of the object. And, you can see temperature, you can see wavelength, you can see Planck's constant. You can program that for any temperature. This diagram is showing where the visible light is in the spectrum, and that each curve is the emission spectrum for objects of different temperatures. And one of the things we notice is that the hotter that the object is, the more radiant power it emits, right? If it's hotter, more energy comes out. And that's the area under the curve, right? So, and it's nonlinear, it's proportional to the fourth power of temperature. And then the other thing we know is that the hotter the object is, the shorter the wavelength of its peak emission. Right? So really hot objects, 7,500 degrees, are emitting here in the purple. Do we know anything that's 7,500 degrees? Turns out the Earth's core. So they always showed the diagrams of Earth's core as red hot iron, which is not actually all that hot, right? If you're emitting maximum in the red, it's only 4,500 degrees. So actually Earth's core emits purple. Right, that'd be awesome to see. Okay, so the sun's about 5,700 degrees, not as hot. So it emits maximally in the green, and that's where we are. So this is a model of the emission. And is that consistent with our observation at the top of the atmosphere? What is it? Tell me what's different about it.
The stuff that the atmosphere, or wait, hold, never mind.
Yeah, we're at the top of the atmosphere. Hold that. You're right, you're on, but next slide, yeah.
Particles in the sun absorb.
Yeah. Yeah, so particles in the sun actually absorb some of this because it's not a perfect black body, right? The other part is that we can really only see the visible part, right? We don't see all of this. It's there, but we don't see it. And so if you just blow that part up, this is what the spectrum looks like in the visible. Does that look like this? What'd you say? What was the color of the sun?
I called that white,
Yes, you did.
but
But look at this. So this is blue to red. Is it approximately equal? Not bad. It's sort of flat, right? Like if you put a spectrum under there and you add that all up, it's pretty white. Who knew, right? So it's pretty white. The sun is. Don't look at it to validate. That's not a good cowbell. Okay. All right. Now we go through the atmosphere. Another of my favorite pictures that I tried to put in everything. So this is again taken from the space station. This is the sun rising or setting, I can't remember. So let's talk about the atmosphere. What can you discern about the atmosphere from this picture?
Pretty thin.
It's very thin. It's so thin. I mean, it is what protects us from space, and we are just messing with it, right? We are just putting gas in there, just willy-nilly, putting aerosols, and it is this teeny tiny little layer. And what else do we know about it from this picture?
Seems like blue light proportionally makes it through.
It's very blue, right? So although the sun is whitish, what ends up, the light that ends up out of that sunbeam is blue. Right? What else do we see from this?
There is spectrum.
Is what?
There is a spectrum of light.
Yeah, so it's purplish up at the top and lighter down below. So that tells you something is changing in the distribution of the color of light as it goes through the atmosphere, as the sun is going through there. Okay? It's not uniform. It turns out it's, there's a lot more atmospheric pressure at the surface than there is at the top, right? So there's just more pressure. So it's uneven. So the materials that are in the atmosphere are not equally distributed. So there's a lot we can learn from this. Okay, so here's the difference. This is what we saw at the top of the atmosphere. Here's what we see at the surface of the Earth. Consistent. What color is the sun? Still white. It's still white. Does it have rays? Does it look relatively uniform in terms of its emission in all directions? What about the sky? It's blue. So if we put something in front of the sun and we measured the light, it wouldn't look white, it would look blue. So skylight is really different in terms of the intensity of light and the color of light compared to the sun at the solar beam. But all of that light ends up in the ocean. But there's very different properties of the light coming from the sky, which is just scattered light out of this beam, compared to what's coming from the beam. And you have to take into account both of them, and the ratio between them changes depending upon a lot of different things. Clouds, angle, latitude. Okay, now we're in the ocean. Can you find the solar disk? Sort of. Depends on how deep you are, right? How many people ever have gone snorkeling or diving and just let yourself fall backwards and just watch the sun go away? If you've not done that, it's awesome, right? Do that, especially if the sun is not quite vertical. If the sun's off at an angle and you watch it, you're gonna see something really, really amazing as you go deeper and deeper, what the sun looks like to you. maybe it's intensity, maybe it's color, maybe it's angle. So think about it. But right now we're at enough that we can see that the sun is still white with this photograph. And what else do we notice? What's happened to the light?
It attenuates.
It attenuates, right? It's a lot darker and more diffuse. You have more light coming in from the sides. We have dark areas, we have gray areas. We'll talk about why we're not getting any light over here, but why we still have light here. What about the color? We've gone from your t-shirt color, what's your name?
Sebastian.
You're Sebastian. We've gone from your t-shirt color to maybe Guillaume's t-shirt color, right? This was the sky and this is the ocean. So we've had a complete change. Everyone's looking around, they're like, well, I'm space. But everyone's looking around like, what color am I? So we'll get to all of these colors actually eventually. So you can see that there are similarities in following the source, but as we get farther and farther away and farther into the ocean, a lot of properties are changing. Okay, here's the graph, my language. So this is the irradiance of the spectral irradiance at the top of the atmosphere, and it's not that smooth curve that we modeled with Planck's constant because of the certain materials in the sun itself, in the outer part of the sun that are absorbing that emitted radiation, and you get these nice lines. Those are called Fraunhofer lines. Now we're at the surface, so what's taking care of the difference between here and here? Top of the atmosphere and surface of the ocean, it got darker. There's like all these places where there's none. So what is accounting for the difference between the black curve and the red curve?
Water vapor.
Water vapor, particles,
Ozone.
ozone, carbon dioxide,
Aerosol. Aerosol.
aerosols, scatter light, absorb light. So we have the atmosphere is taking out wavelengths, some selectively, some just sort of overall magnitude. And so we'll have to learn how to account for all of that. And then the difference between the sun at the surface and 10 meters below the ocean surface. What's the biggest difference that we see here?
There is no light after 700 nanometers.
It's gone because of
Water.
water. So water just gets rid of all of this, which turns out to be tremendously helpful. Because if you happen to detect light, say at an airborne sensor in this region, you know it's not from the ocean, right? So that says, oh, that's how much is from the atmosphere. And then it kind of helps you move backwards into the other part of the spectrum. So people take advantage of the fact that water absorbs everything to get to understand a little bit more about the atmosphere. So that's incredibly helpful, right? And then we could do 1 meter below the surface, 10 meters below the surface, 50 meters below the surface, and we'll see differences in the intensity and the color because we have not only just water, but also all the particulates, phytoplankton, bacteria, zooplankton, organic detritus, sediments, and we have dissolved constituents. And so they will account for changes in the spectrum of light as it propagates through. All right, so let's do some thought processes or some little thought experiments. Okay, let's pretend we don't have an atmosphere. We call it the Howard-Gordon notion. That's how he started all of his modeling was. Yeah. What would the color of the sun be if we didn't have an atmosphere? White.
White.
Right, so we always see the sun as yellow. Where did that come from? It's not, it's white. Okay, so that's gonna be white. All right, what's the color of the sky? It's black, right? And we have our sun over there. So if I asked you to sketch the angular distribution of the light coming to the surface of the ocean, what would you draw?
Same as the top of the atmosphere.
Same as at the top of the atmosphere, exactly. And so what are the beams gonna be looking like?
parallel with the right.
all parallel and direct, because the sun is so big but so far away that by the time it gets to us, it's essentially parallel. So we would see a white sun. So from now on, I want you always to have your suns be white. Tell your friends. The color of the sky would be black. And then we would have the beams of light coming in at sun angle, right? Excellent. Okay. Now, in the presence of the atmosphere, sun,
Questionable.
questionable, because it can also be redshifted because we have sunsets, right? And so the sun can actually change the color depending upon the angle and how much atmosphere it's going through. So we have to be careful about that now. And the color of the sky. Gray. Depends, right? It depends. But we'll say for the most part, when the sun is relatively high in the sky, it's often mostly blue. Okay. And then the angular distribution of light, well, we still have a solar beam. But then we have light coming in from the skylight, right? So we have to account for the fact that there's all of that. So I have those beams, and then this blue in the background is meant to be light coming in from the sky in other directions. So it gets complicated. Okay. All right. So the atmosphere reduces the intensity of the source. It changes the color of the light coming in. It changes the angular distribution of the energy coming in. And so when we get to the radiometric properties lab, you're going to look at natural variations. You're going to compare radiation from the solar beam versus the skylight. And you're going to look at the angular distribution. And then we'll be able to like really, really say something about the source and the light that's coming in. All right. So now we're at the ocean surface. We have our white sun, we have our beams coming in. What happens at the surface? Well, we have an incident beam, and then what can happen to that,
Reflects.
It can reflect. Right? You said it in the exact order that I would have said. Yeah, reflects.
Can refract.
It can refract, which means that it goes through the interface and goes down. So we'll talk a lot about all of these terms and what controls them. I've got a nice flat surface, so things are much easier, right? And we'll talk about what that angle is. It doesn't come in at the same angle, it refracts, it bends. Talk about why that is. Okay, so here's something about surface reflex. So this is a photograph taken from space. This is the Indian Ocean, and this is a lagoon. And what you're seeing here is the reflection or glint of sunlight off the surface. So, right, if you don't have polarized sunglasses and you look at the ocean, you get that white glare. Well, look at this is what the satellite is seeing all around it, and then this really spooky glint in here. Whereas if you looked at it from another angle, it looks like this, which is just, it's just amazing what glint can do. So you can imagine as a remote sensor, you want to figure out how to not have glint, right? So we'll talk about how to do that. Okay, so now it's penetrated the surface. What is going to happen to the light as it's going to the surface? What are some major processes that are going to be driving how light moves through the ocean?
Absorption,
Absorption,
scattering.
scattering. One more thing.
Transmittance. Transmittance.
So it'll be transmitted if it's not absorbed and scattered.
Re-emitted.
Re-emitted, yeah. So we have absorption. Absorption removes light. So if you were drawing a little diagram, how would you demonstrate that absorption was happening here on my diagram? Yeah,
I would change the arrow size as it goes through.
right. So you can start off with a big fat arrow and you can narrow it, right? So think about how you schematically represent a process. And if you are consistent with how you do that, then all you need is pictures to describe more complex things. Okay. What about scattering? So scattering redirects light. There's no loss in energy. So how would you demonstrate that in a diagram?
Lots of
Arrows
arrows.
to branch out.
You would change the direction of the arrow. It could be multiple arrows representing the probability of scattering in different directions. It could be like one arrow, like one event happened and one, packet of energy moved in this direction. So changing the direction of your arrows without changing the size demonstrates scattering, okay? What about re-emission? So that's fluorescence is an example of that. Fluorescence is the absorption of light at one wavelength and the re-emission at a longer wavelength. So how would you draw that one?
Just the color,
Pardon?
just the color.
Change the color, exactly. And you can also change the direction because it could be absorbing energy from here and it will re-emit maybe uniformly. So you would want to change the color and maybe the direction as well, right? So now you have some tools to start drawing things, right? So you see where we're going with this. Okay, good. So let's do some practice. So I want to consider an ocean that has no particles, so no scattering. And I know that water molecules scatter, but we're going to ignore that. We're going to pretend that there's no scattering, there's just absorption. And you can either be on the vessel or you can be the diver. You can be both. So I want you to think about, what do the sailors see when they look at the ocean? And what does the diver see? Okay. So give it a try. If you guys work with the people sitting around you, I want you to think about, what does the sailor see? If there is no particles, there's only absorption, there's sunlight or whatever you want to have come in, sunlight, skylight, you can pick a wavelength, I don't care. You're looking over the side of the boat, what are you going to see? Go. Go ahead and discuss. Think of reflection, you can also think of steps you take back out of the surface from the interior to be reflected.
He's saying it's clear because there's no particles, but it does have absorption. Right, then what's absorbing, it doesn't.
Like maybe we'll. And so all the
Yeah.
What do you think? What do you think the sailors are going to see?
Purple,
Why purple?
there's nothing to reflect the light back up, so as water absorbs, it kind of absorbs.
So when you look over the side, you'll see purple. How many people thought that? So if you had something, so something that didn't absorb purple.
Yeah.
Right, so there's something about the absorber that you've decided didn't absorb the purple light. Okay. So given that, is that what you guys all found?
There's also going to be reflectance that will be unaffected by absorption by water that the ship would see.
So reflectant, say that again.
Reflectance that comes down is reflected immediately off the surface, so it's not necessarily absorbed readily. So it would be representative of the original source light.
So there could be just a surface reflection because there's a difference of an index of refraction. So what color would that be?
White-ish.
Okay. Okay. What if you were looking at an angle where there wasn't any?
Purple.
Okay. But I didn't tell you what the absorber was. You assumed water. I know, you did, right? It's okay, we're in an oceanography class. What if I said it was an absorber, it could absorb all the wavelengths?
White?
Why white?
Well, if it's absorbing everything equally and we just kind of like chop off the bottom bit, essentially, we would still have an equal amount and it would be essentially level. We need to remove one section of wavelength to change the color.
Right, so if you remove a section because your absorber maybe only absorbs one, but if your absorber can absorb all the wavelengths,
If there's no scattering, nothing would ever come back on the surface. black.
Mhm.
Except for the sky was like.
I just absolutely don't.
You don't see, I see where you're going, like there's something that's happening here and then there's more here and there's more and there's more, right? But when you look over the side, you don't get to see that unless something redirects that back to your eye, redirects it back to the ship. But what would redirect the light?
Scattering.
Scattering, but I told you don't have any scattering. Right. So what seems like, oh, I'm certain I know, it's sometimes your intuition is not right there. You have to like really think about the fact that if there's nothing to scatter and there's nothing to reflect off the surface, that's what you see. But what does the diver see?
I feel like they would have.
So if the diver's right here, we get back to something that you were thinking about.
It would just seem like clear. Or you'd be able to see up but not down.
When you look up, so say you're 5 meters down and you look up and you have an absorption coefficient that absorbs all of the white colors equally. You're 5 meters down. I haven't told you what 9 meters, but say it's absorbing like 10% in 5 meters. And you look up. What do you see?
Weaker white light.
Yes. And when you look down, what do you see?
Black.
Right? And so it depends on where you are when you're looking up, right? It would get, and I had it as blue, but depending upon the color, it could be gray, right? Going to black. But you look down and you don't see anything. You see black. But you look up and you're just watching the sun disappear away from you. So, is there a natural analog? Yes, of course. So there's this really great place, the Rio Negro. This is an image from NASA, and it's where these two rivers come together near Manaus. And this is the Rio Negro, and this is, I think, the main stem of the Amazon. And you can see very distinct coming together of these two rivers. And what does this one look like? Right? And so if you get up close, you can see that it's just CDOM, colored salt organic matter, which is very effective at absorbing blue and green, and water is very effective at absorbing red. And when you put them together, the water essentially looks black because there's no particles. Right? And here, where there's a lot of sediment-laden material, there's also a lot of CDOM in there. Don't let it fool you, but there's so many particles that are scattering the light back that you can see some of that color that you don't see here. Okay? You're scowling at me. Okay.
I
good.
just
Okay,
do
good.
that. Yeah,
It's
that's just
okay.
how I
Give me a
am.
smile. As long as it's not a question.
So by the way, you're gonna see it in Maine. We have
Yes.
a lot of unique lakes and
Yeah.
unique ponds around.
How did I
where
lose
you
my
drive.
And there's a place called Sun Cay Stream, which is up on your way to Orno, and you can put your hand in the water and not see your fingers. It's so much CDOM. It's really amazing. Okay, so now we have no absorption. So there's water, but it's not absorbing in this scenario, but it does have particles. And we'll see that the particles scatter light equally in all directions. Okay. What does the sailor see? What does the diver see? Okay. Sailor looking over the side. What do they see? Talk to your group.
Yeah, making white, but like, it's like
Like
there's no particles.
Oh, like as a
There are
scatter.
particles.
Yeah, every time.
Oh, thank you. I can't read.
In the water.
It was so good.
I'm standing.
No,
Like the diver would probably see
water if it's
white, but if you're looking
Which are
Like the space is white.
just depends on how much.
So you're not worried about what wavelength this is absorbing?
Because
It's just going to whatever it is, it's going to scatter it
Yeah, exactly. So it
The
might
diver would also.
directly coming in. Like you're saying,
Yeah, underwater radiation.
Because it's not absorbing.
Yeah, exactly. And maybe it's the radiation, yes.
Right, because it's like,
I think it depends on how the concentration of
but it
particles.
would
Or
also.
Yeah, there's like low particles are probably.
All right, what do you think? What's the ship see? Look over the side. What are you gonna see? I think everybody got it.
White,
Wait, why?
it's reflecting in all wavelengths.
Yeah, so it's scattering all
They're
wavelengths,
scattering.
and some of those redirections will be in some directions, some will be in others. But if you're looking over the side, what you're seeing is the part that got scattered back out. And if it's scattering all colors equally, that's white light. Right? So if you look over the side, you will see white. Okay, what about the diver?
Also white,
Why?
because there's nothing to absorb it to change the color.
How deep did you go?
Probably, I don't know, as deep as it is.
Right, as deep as it is.
I had a different theory, and that was that it would decrease because you'd get initial reflectance that would bounce it out, and then it would only have so much light that wasn't reflected back up. And so as you went deeper, the light level would decrease, but not because we're absorbing light, but because some of the light has been removed from the system back to space.
And you guys going to go right in that hole. So if you think about sort of like a pulse, maybe, but if you think about this constant amount of light always coming in, right? And I also didn't tell you the angular distribution of light, right? Like we don't know how much gets scattered forward and backward, but we have multiple scatterings. So if it's coming in one direction, it gets scattered in the forward direction. It could get scattered in the forward direction, or it could get scattered in the backward direction. So the angular distribution, but it turns out you could make the ocean bright all the way down if there was zero absorption. Because there's no loss. And so you get an equilibrium of light coming in and light coming out. So this is kind of the theory of an integrating sphere, and we'll be working with an integrating sphere this week. It's very interesting because it's very counterintuitive. So natural analog, yeah, a misty day, which you'll see. So that's particles in the air. There is some absorption, obviously, because it's water particles. We can also think about sea ice as being a very thin, representation of being very highly scattering. And although absorbing, you tend to see, because the scattering overwhelms the absorption, you tend to dominate by the scattering, so it's a good analog. Coccolithophore blooms, right? And again, they don't look totally bright white from satellite because we do have water and they do have chlorophyll, and so there is some absorption, but again, their scattering is white scattering, and so it tends to really amplify. They're only about these particular species are only about 2 microns, coccolithophores. They have calcareous plates, calcium carbonate plates that they plaster all over the cells that are highly scattering, highly polarizing too. And this is an image that I found. It's very hard to find an image of someone like in the middle of a coccolithophore bloom. But these people happen to see it. They're from north of the North Pacific Ocean, I think, off of Vancouver Island. And their water is normally sort of dark and kind of grayish looking. And then all of a sudden one day it was just bright and tropical. They're like, why are our waters suddenly tropical? Well, they had a big coccolithophore bloom. And so it brightened the water incredibly. All right. Oh, and then the last one would be glacial flower. So this is up in Banff in Canada, and the lakes are like milky colored, and it's because the glaciers scour the rocks and deposit tiny little particles that stay suspended in the water. And so depending upon, it turns out the size distribution of the particles that are in there, because it turns out scattering does sort of depend on the size, it can change the color from a milky blue to a milky green, depending upon the size sorting of particles. So, so yes, definitely natural analog. Okay, so these examples, I've been talking about the white, the whole visible spectrum, but I think what's really important is to understand that within narrow wave bands, certain wavelengths, the ocean may behave as a pure absorber, where absorption is so high and scattering is so low that you can model it in that wave band as an absorber. And there are other wave bands where the absorption is so low and scattering is high, and so you can model it as a nearly perfect scatterer. Okay? And so that changes over the spectrum. So depending upon what wave band you're in, you can make some approximations that can really help you understand the processes giving rise to the light field. Okay. All right. So, say in the infrared, we already talked about that. Water is such a strong absorber. And if you're in the open ocean, away from phytoplankton, very low concentrations of organic material, it can look more like a pure scatterer in the blue. Scattering will dominate the process. All right. So I just want to show you an example. This is the Gulf of Maine. This is an image I took off the Gulf of Maine in September. This is the reflectance coming out of the water, the intensity at 412, and I color coded it. So it's very bright blue offshore. You get less and less darker blue light and almost no blue light the closer you get to the coastline, because of course we have rivers with high sea dome and it absorbs all the blue light, right? If we look at another channel in the green, you can see there's a range. It's very bright off here, something going on off here, where it's bright green, but then the rest of the Gulf of Maine is mostly just green. We tend to have lots of sea dome in the water. But then it's very bright along the coast because particles are scattering the green light. And then in the infrared, it's just black. Right? So it's behaving differently in different regions at different wavelengths because of what's in the water and that sort of that constant pull between absorption and scattering. All right. So from space, we tend to see these like beautiful variations in color. I love this image. It's in the Barents Sea, it's phytoplankton bloom. You can see the physical control of the blooms because of the dynamics, but then the color varies based upon the concentration, the composition of the materials in the water, and it gives rise to beautiful color images. Is anyone familiar with Clark Little? I always have to show this. He's this guy who just gets into the wave zone with a camera and lets waves crash over him. Look him up, he's got video now, it's awesome. So he's got these giant waves off of Hawaii. They change in color, right? So absorption, there's a lot of sea dome in that water. That's right where one of the rivers comes in after one of the big floods. And then I love this one because you can see the resuspension of the sediment. You can see like individual particles, and here you can literally see through the wave. Like so, this is melange of absorption and scattering. Anyway, okay, so now here's what I want you to do. You guys are going to be at this board, you guys are going to be at this board, and you guys are going to be at that board, and you guys have to move out of the way. Okay. We have some vocabulary. I want you to take a few minutes, and I want you to consider a beam of light coming into the ocean. And I want you to think about the processes that impact it, so that if we were going to measure the light here and the light here, what is happening to the light in that distance along that path? Okay, so let me think of where I'm at. Okay, so I want you to describe it or sketch it or do a schematic or whatever you want to do, but just think of everything that's happening between here and here, and go ahead and put it on the board. So I'm going to give you guys 5 minutes to just write down some processes, draw some arrows. Like, open doors so they're not so. Which one is it?
10:18.
I have a green color.
Oh, we're gonna red.
Red, we've got some blue.
It would be reflected.
Sure. So start with
And if you want, you guys can break it up and do two groups if you feel like it's hard and not enough people are getting to draw. Everyone should get pen on board.
We can do this in multiple ways, though, like some other thoughts, like we can have the diagram, equation, graph, like.
We can write.
So.
Beam of light. Are we're just tracing one beam?
So feel free to like spread like circles out and each of you can.
Yeah.
All hands are
everywhere.
Yeah.
For absorption, I guess we can just draw arrows like that from this.
I usually just do a point.
Or shorter.
Yeah, sure. What are you thinking?
I just do it one type, like a part of it, so this is my.
Oh, yeah, sure.
Oh, very nice.
You mean doing the ocean?
It doesn't leave here, but leaves.
So this is the absorption.
And then I'll draw two.
Very hard.
Just
Yeah,
add another arrow, yeah.
Yeah. Well, you know,
That's fine, that's fine, that's
it's
parallel.
new, that's new. It's new, very practical.
And then just arrows all over. Or.
And if you're not happening to be one of the people drawing the arrow, you can make the list of the processes too.
Yeah.
Okay.
That starts to become like, you know, beginning of a description or an equation. If you want to represent it mathematically, go ahead and guess at that.
I know we're tricky.
We just wanted to.
I was just writing not being considered. Or you could do like a diagram. That's nice.
I don't know what like the.
So maybe you should do like a practical, like a large arrow, and then have a thinner arrow.
We take points out of that.
Yeah. Yeah. So then did that on that.
Yeah.
Yeah.
If anyone wants to take a guess at what that mathematical like
Yeah, I
representation.
have never processed it on
Yeah, it's just
Yeah.
But here.
Oh,
Yeah.
yeah.
It's just immediately reflect.
Yes. Yeah.
Then we.
Feel free to include the English, it's awesome.
Well, reflection is.
Like instant
No, this is a fake.
That's what I did.
Yeah.
Yeah, reflection is.
It's two different, like it's and then something else. Maybe a different color.
Right.
And then you can have two colors.
So right, actually. Blue, right?
You want to do scattering as.
Yeah, they have this, I mean, some of them are. Yeah. Scattering, isn't art something? Yeah. There's radiation. Anything around.
Maybe related to the scattering. Overall, like.
Yeah, just like,
Oh, diffusion.
just like that. Smaller and smaller. Yeah, that's
Is that the chloroplast or what?
We put it as minus or are we assuming it's negative?
Yeah, yeah.
I
Oh.
think it's like,
That's negative. Okay.
So you guys can make a list, if you're not doing it, make a
He was
list
saying
of the
the
processes that are happening.
Yeah, yeah.
Take a Greek guess at what you think that
Oh, I love it.
yeah, represent that.
She does say, doing as a function of death.
yeah.
I was like, oh, I know what I do.
Yeah. How does all this change?
Another circle, and circles. We did like, we just drew like an overall thing. Yeah.
Oh,
Well, maybe we're supposed to start this on that.
yeah.
There you go.
Yeah, I think those are also.
That's true.
All of these processes. have
Yeah.
to-
Yeah.
Yeah, it's gonna happen, like, for
Oh,
Well, yeah.
Oh, yeah, I don't just see it by.
I think it's kind of relating, depending on the. Depends on.
Oh, guys, oh no, we got reflection on that.
Yeah.
Okay.
Yeah, we're
Oh, yeah.
you integrate it.
Yeah.
Oh, I got P.
Oh, it's. What do you have? C.
It's like what?
Yeah. How about you can ask me?
Well, I did the level.
Oh, we have one of our.
Yeah.
Is it the deadline?
No, this one.
Yeah.
Yeah, that one.
What's the equation?
Okay, so it's good to know, so, you know,
Yes.
they've sat for a year.
It's been a while.
It's not.
I feel like we need to.
You can do the same for yours.
Yes.
Yeah. More.
Because we're assuming, oh no, we're assuming I'm
Yeah.
on a zero.
So,
Yeah.
yeah, we can separate.
Radius
Yeah,
of
that's
surface
that's
area.
very
Yeah.
nice, yeah.
Oh, yeah.
This is total, sorry, this is total scatter, this is total instead of function. Oh, that's right.
Yeah.
Nice.
That's exactly what I was thinking.
So we can count on process as a usual.
Absolutely.
Scattering by definition preserves the original wavelength.
Yes.
But then, I thought the one that's what is elastic or inelastic.
Yes, so fluorescence and Raman are inelastic, there's loss of energy, right? And that's why it goes to a different wavelength, right? Lose energy, and
Do we assume there are more
so
particles
it
at the
has
surface?
a different wavelength, and of lower energy to us is rich, from its original. So that's the elastic is like.
Linear decrease?
So it is a
I have no idea, I'm guessing.
Yeah, it's well, like, it depends on who you talk to. You know, it's like, if it's absorption and re-emission, it's scattering. So.
Just a straight line down?
I mean, I guess.
But yes, inelastic.
Straight line down?
Okay, take just a couple more minutes and then we'll.
Yeah, that, I mean, if we're assuming it's water, right? Or are we saying the absorption is happening from particles or from the water?
Yeah, I don't know. Like, I
Because
did.
I think it's
not
kind
a
of
straight line,
impossible.
but the particles would be based upon their distribution. Yes, and the type of. Oh man, there's no type of
Yeah, we're gonna get drawn.
We can put a question mark there.
Yeah.
Yes,
There you go.
absolutely. Because it's really just the first morning of 4 weeks. And if you knew everything, I would think like, you should sign up here. All right,
They've done a great job.
let's do the big reveal. free to look around and see everybody else's interpretation.
Yeah, I'll put it up there.
I
Oh,
see
they have a
we
lot of
have
equations over there.
some phytoplankton over here. We have an anglerfish over here, anti-thermal vents. And we have a Secchi disc over here, so we definitely have some figures. And I see arrows representing different processes of light. And so essentially what I asked you to do is, spec out the radiative transfer equation. Because really, all the radiative transfer equation is a mathematical description of how light changes from one depth to another. And what happens in that depth interval, and it could be infinitesimally small, so we can use derivatives and stuff. Or it could be like, oh, I can measure at this meter and that meter with my sensor and figure out what's happening in that meter in a bulk sense. But that's essentially what the radiative transfer equation is. And so before we go a little bit further, because I'm looking and I'm seeing absorption and scattering and re-emission, and it's happening in this direction and at this wavelength, and my arrow's getting bigger and smaller and changing direction, and I've got different things in the water that are doing different things to it, and it's happening differently with depth. And I have I don't know if we can partition this. I don't know what that graph looks like. But I know that it's something. I know that something is happening in this process, right? So now I want you to take part B. Now that you have done this, and you know that what you have done is discuss the process and properties of the radiative transfer equation. For yourself, has it changed where you are here? And it's fair if it has or it hasn't, or suddenly you thought, right, I know just what to do, and now you're like, oh my gosh, it's so much harder than I thought. That is fair, right? Let's flip it over. Okay, so we're going to talk about it, and we're going to talk about this beam of light, and I should have been, picked a wavelength that's not a combination. We could have picked a pure color like dark blue, but it didn't show up on my picture. So I've got this light color arrow coming in, and we're going to call that radiance, and it's actually coming in at a certain direction. It could have come in vertically, it could have come in horizontally, but we're going to follow it, along a path. So we're looking at like a small angular distribution of that light. And we're going to spend way more time on this, so again, you don't have to write this down. And it's traveling along a defined path defined by that angle, and we'll tell you what those angles are. I'm not going to tell you now. And I asked you what impacts that light, and you told me what's impacting it. I see absorption, absorption, absorption. Okay. So absorption. So what does that do to the arrow? Makes it smaller, right? So it's going to make it smaller. Right? And I'm actually going to show mine as I go down, but what you have done is actually shown what happens between here and here horizontally, right? And I'm going to pretend that this is my area of things that can happen. Okay, and then you also said scattering. So if I have scattering, what's going to happen to my arrow? It's change angle, right? So it's going to go in a different direction. I've scattered out of the beam. So if I'm measuring this light in this angle, I suddenly don't see this anymore. It's gone. It's somewhere else. The person who's measuring at this angle, right? But I am no longer seeing that. So I'm seeing less light from absorption. I'm seeing less light because of scattering out of the beam. But here's the thing I want you to consider. What about something that may be scattered here and got me back into the beam from some other part of the light field? So we can have scattering into the beam from light coming in at a different angle. And that would look something like this and end up here, and that would add some light. Right? It is cool, isn't it? Because you have to think about, we have this horizontal distribution of light, and we have probabilities that things are going to be happening. So we can lose it to absorption, some part to absorption, we can lose some part to scattering, we can gain some part from scattering. And then what's the last thing we have? I see fluorescence. I see fluorescence. I see,
Remission.
yes, reemission. Right? So part of the light that can get absorbed, either here or maybe next door, can contribute from one color to another, from purple into blue, get the seed on. Okay, and so that adds light. So if we squish all this together, we can have a beam, we can have radiance that changes differently depending upon the processes that are happening in that path. The radiative transfer equation describes that. It describes those steps. And it turns out that if we're looking at radiance, and we did say it's coming in at an angle, we're looking at the change in the radiance as a function of distance along this path, d radiance, dr, distance along the path. We actually usually measure as a function of depth, so we're just gonna have to do a conversion there between this angle and the vertical angle, because we're doing this as a function of depth. But if we know what this angle is, we can, you don't need to write this down, you're gonna have plenty of time to do this. We can just come up with the relationship between the cosine and the vertical versus the path, right? And so this now becomes the cosine of the angle of that radiance, and we're looking at that, the change in that as a function of depth. So absorption, the term for absorption is really simple. You have a certain amount of irradiance, you have an absorption coefficient, you multiply them, and that's how much radiance was absorbed, right? So there we go, and it's a loss term. So that's that arrow. Scattering out of the beam, same thing, it's a loss term. You have so much radiance, you have a scattering coefficient, you lose that much. Scattering into the beam is a little bit more complicated because it could be coming from this direction and scattering, coming from this direction and scattering, coming from this direction and scattering. It could come from anywhere and scatter in. And so what you have to do is figure out what the angular distribution of scattering is and integrate it. It gets really complicated. So it's a little bit bigger term, but we'll talk about this. But essentially it's a description of the scattering from all directions times the radiance at that direction that it was coming from into your direction. And you integrate it. So it's a term, but it's really just all of the contributions from scattering from other directions back into your direction. Interest. And then this last term is how much light was absorbed at the wavelength that it absorbs times whatever radiance at that wavelength that ends up being emitted at another wavelength. So there's a term for that too. It's a spectral term. So you have to keep track of direction, we have to keep track of wavelength, and then we just need to know these terms. You put it all together. That is the radiative transfer equation. You all did it. You did it here. You have all the terms on there. You may not know what the depth distribution is. You did know that light is exponential with depth, both did, right? Like you have all the terms there. You maybe just didn't know like what this term is, but you can describe the loss already, and we're only in the first morning.
Are absorption and scattering not spectral?
Yes, they are, but they're conserved, right? The light at 440 gets absorbed by the absorption at 440, right? So it's there. They're implied spectral. There's not a change in the spectrum. Yeah.
Also from just this equation, what should be the units of absorption and scattering to be consistent?
So we're looking at change
Inverse meters.
inverse meters.
Inverse length, for example.
Yeah.
Because in an equation, all terms have to have the same units.
So, welcome to the class.
Sorry, do you want to explain the last term one more time?
Yes, the last term. You have absorption, say by sedum.
Mhm.
It absorbs in the blue. And it re-emits at a longer wavelength. There's some loss of
Okay.
energy. And so, and usually to heat. And so when it re-emits, it will re-emit at say blue. So I drew it as it absorbs sort of purple blue and it re-emits at sort of greenish blue. So that's what CDOM does. And so you're measuring this wavelength, whatever color this is, 460 nanometers, we'll say. You're measuring that. CDOM over here absorbed way farther bluer wavelengths, say 400 or 370 or something like that, but then re-emitted in all directions at the wavelength that your detector is measuring. And because it will do it relatively uniformly, some of that's going to end up adding to the light that you're trying to measure with your small angle detector. It will now, and so the absorption from here shows up in this equation at that purple wavelength right here.
Okay.
But it ends up emitting in the blue wavelength in this equation. So we have one of these equations for every wavelength, and we have one of these equations for every wavelength at every angle.
Okay.
That's where it gets complicated. You have to keep track of where you're looking at the radiance and what color you're looking at it in.
Okay.
So you can imagine if we were resolving some sensor that had, I don't know, 82 wavelengths, and we could resolve at 10-degree or solid angle of like 10 by 10 solid angle, we would take our radiance sensor and we would be like, okay, we're only going to look at this angle, or we're only going to look at this color, and then we're going to change the wavelength, and we're only going to look at that color. Oh, but now we're going to go over here and do all the colors again. You do all these angles and all these angles.
Okay.
And
Got
it's
it.
hard
That's a lot of
to do that.
Gotcha.
You can model it, and you're going to do that in Hydrolite.
Mm-hmm.
And there are, types of sensors that allow you to have a fisheye lens. You can measure radiance over a whole, set of solid angles, and you can put different filters and get different wavelengths. But it's a lot of work, right? You definitely want to jigsaw that. You want everyone to have responsibility for one angle and one color if you're doing it by hand.
Okay, so it's sorry, one more question.
keep
So, do you usually measure all angle? Is it pretty standard to measure all angles at once with a fisheye equipment like that?
If
or
you're Ken Voss, yes.
Okay.
If you're Ken Voss, you have that 2 of a kind, 1 of a kind sensor.
You're right.
So what we have, and what you guys will get to play with, is a sensor that basically has a field of view. We usually have it looking at the light coming up, right? But you can take it and you can say, I want to look at that skylight. And I can look at the skylight coming in here, and then it'll refract across the interface, and I'm going to look at it and I'm going to lower it down. You could set the angle and do that.
Okay.
But to
Or
get
we
the
integrate
full,
a hemisphere, or we integrate a
we
hemisphere.
do the whole hemisphere. We say what's, instead of just doing one angle, let's just do all the downwelling light. Just see how that disappears with depth.
Okay.
Yeah.
Okay. Thank you.
Because it's a lot to keep track of. It's a lot to measure, and you have to design some pretty fancy sensors to do it.
Yeah.
But we could do some interesting things with detectors and creating cones of light at different angles and measuring them.
Oh, cool.
We do
We
that
have
with a
some
tube.
work to your generation.
Yeah.
Okay.
Your homework for your life is to design that and make it commercially available for all of us. Yeah, question.
Could you just describe the left-hand term again, what we're measuring?
So what we're measuring is there's a certain amount of radiance coming in, and we've measured it here. And we're gonna measure it here. And we wanna know what happened to it over that depth interval, which could
Is that
be
DZ?
infinitesimal, or it could be a meter. All of these processes are happening horizontally uniform. I've shown them as it does this and then this, and it doesn't. It's, some of it gets absorbed, some of it gets scattered in, some of it gets scattered out. But what's happening in that layer of water is some of the energy is absorbed, some of the energy gets scattered out of the direction of which you're measuring, so you don't see it anymore. Some of it gets scattered in. These are not always equal. And you can get light coming in because of fluorescence into your direction and into your color. So we're just looking at all of those processes that are impacting light and depending upon the magnitude of absorption, the magnitude of scattering, the angular distribution of scattering, each of those properties, the inherent properties of the water, defined by the phytoplankton, the mineral particles, the sedum, the bacteria, the detritus, those things are going to drive those properties and therefore impact how the light moves through the water and what angle the distribution is and how much it decays with depth and what colors decay faster or slower as you go deeper.
My optics class t-shirt has that equation on the back.
Right.
And a Princess Bride reference.
Excellent.
And I would comment, what you guys just did on the blackboard is exactly what the founding fathers did a century ago. They just sat down and thought of like, well, you know, there's this term, well, yeah, we ought to include that. No, well, then there's this other like scattering thing. But at that time, you know, in 1900, they didn't even have definitions for absorption and scattering. It was just like, well, you know, some of the light's going to disappear. And I don't think this equation, as she wrote it, was actually ever put on a piece of paper till the 1950s. And anything before then, if you read literature, they always assumed, well, it's non-absorbing or it's non-scattering. To get an equation you could solve with pencil and paper. And it wasn't until the 1960s at the earliest when people like George Cadwar used Monte Carlo techniques to actually start solving the radiative transfer equation on a computer, which is, you just can't do this with pencil and paper. And so this is not stuff that goes back to Newton and Copernicus. This is actually, you know, within my lifetime that you could even think about solving this equation and not have to make so many assumptions that it was completely useless for the ocean. So it's really pretty new science here.
You know, and also, you know, they had to make those assumptions, which as you guys demonstrated, at some wavelengths, those assumptions aren't bad, right? If you're in the infrared, you could just assume that it's absorbing. You could get rid of these terms, right? And it becomes relatively easy to solve. Or you could get rid of, you could pick a wavelength for scattering dominance and you can get rid of the absorption term and only deal with scattering. You know, but the reality is you're kind of dealing with all of it all the time. But at least you can make some approximations. And so, you know, it's always good to have those processes in your mind when you're making a measurement and you want to just sort of check it. Like, I think what I should get is this because I've thought about it. And then you make your measurement and you're like, oh, okay. Or you think, ooh, I didn't get what I thought I was going to get. So either I made a bad measurement or I had some bad thinking going into it. But it's always good to sort of think about what you should get before you get there or make your measurement. All right, we're done for the morning. So what we want to do is be ready for our COVID test.